We're talking about energy, and we established a formula for figuring out energy in the electrostatic field. And the way we establish the energy in the electrostatic field is through figuring out how do we build a particular configuration, whether that configuration is a bunch of discrete charges, or that configuration is a distribution like surface charge density distribution, volume charge density, or line charge density. The idea is that we assume that everything is beyond infinity, and then we bring it in one by one. So we build the configuration one charge at a time. And when we went through that exercise, we discovered that W equals half sum I equals 1 to n of Qi Vi. When we go to a distribution situation where we have a charge distribution, this sum turns into an integral. So W becomes half integration over V, rho V, V, the voltage at every point in space, dV prime. This is dV prime, okay? This is integration over a source, okay? So this is good and all, but this kind of ties, we need this form of this equation for energy ties two things, ties the voltage distribution, charge distribution, and the field, the voltage. So that's good, we can use this, but the question is, can we describe energy as a function, of only the fields? Right? So here, instead of having a mixture of charge and field, rho V times V, can we describe energy in terms of as a function of only the field? Because it is the field that acts kind of like the spring in a mechanical system. It is the field that really holds the energy. Okay, and yeah, to conclude our discussion on energy, this is what we will go through today. So, okay, so this is kind of like a review of what we did last time. So can we calculate energy from E, D, or V? Remember, all three vectors, fields, or scalar field are equivalent. The calculation goes something like this. So let's start with rho V. Rho V is the most general thing we can consider. Right, so this is some mass with some charge distribution, rho V, and this is R equals infinity. Okay, and we will shift our perspective a bit. So the integral for energy is over the source, right? V prime, rho V, V, dV prime. That's how we derive it. Okay. Would anything change if we change the integration from V prime to the whole of space V? Nothing will change if we do the integration this way, and the reason nothing will change is because everything is zero anywhere. I mean, rho V is zero outside of the charge density. So it's kind of like you're integrating this function, x, fx. You're integrating it from A to B, fx dx. Does anything change if you change and the function is zero outside of A, outside of B. Does anything change if you change your limits of integration from C to D? No, nothing changes. It's the same resultant value. So this equals integral from C to D, fx dx. So nothing changes if I integrate over all of space. Okay. So now we want to get rid of rho V. The only way we know how to get rid of rho V is to use postulate 1. So postulate 1 states that divergence of D equals rho V. okay, which is divergence of epsilon E equals rho V. Okay, so that means that the energy now is going to be half integration over the volume, the whole volume, this thing, which is an infinite volume, but bear with me. I mean, assuming we're integrating over whole space, all of space. The point is that this integration is going to have a limit. It's gonna amount to something. It's not going to be infinity. So this is going to be divergence D instead of rho V times V dV. This looks like something that has a differentiation occurring and then a scalar. So this looks like something where we can apply the Leibniz rule, the product rule, right? So applying the Leibniz rule, I forget if his name has his T, is it Leibniz or Leibniz? I think it's Leibniz. Okay. And we use this form of the rule. So we use the form of divergence V D. If you have a scalar field times a vector field, this equals V times divergence D plus grad V, the gradient of V dot D. So we're going to use this substitution. So this is the same as this, right? So you can move this to the other side, and we get divergence minus gradient dot D. So I can rewrite the integration. W equals half integration over V, divergence V D minus grad V dot D. dV. Again, this is across all of space. So I can divide this into two integrals over all of space, divergence VD minus what's, by the way, grad, what is E? We remember we established that E is minus grad minus gradient of V, right? That's a relationship between E and B. So V, gradient of V equals minus E. So here, instead of gradient of V, I can substitute minus E, the field E, right? So this becomes, the minus cancels with the minus, this becomes plus. I integrate over all of space, E dot D. This looks interesting. This looks like you know, power and energy always has a square in it, right? Kinetic energy has half mv squared. This kind of looks like a square term where you're multiplying the electrical field with itself. So this is suggestive that this is now the energy of the electrical field. But the problem is that we have this pesky component. Hopefully, this goes to zero. And the way we can show that this goes to zero is by using the divergence theorem. Okay. Okay, so we can use the divergence theorem here, but the question is, what is the boundary? So remember, what is the divergence theorem? The divergence theorem states that if I integrate over a volume of a scalar field that comes from a divergence, right? This equals to the closed integral over the boundary. So I have this volume V, and then I have the boundary, the surface boundary of it. So I integrate over the boundary enclosing the volume, D dot ds. Okay. So this is what the divergence theorem states. So if I use the divergence theorem for this integral, what do I get? Let me write W back again. So it's going to be, this is going to turn into a surface integral over the boundary. But this is interesting now, because now remember the volume is all of space. So now the boundary is this infinite boundary, is this infinite surface at the end of space. Okay, so this is S, the boundary at the end of space. This is at R equals infinity. Vd dot ds plus half E dot d. Now, all indications state that this might turn out to be infinite for all we know, right? Because we're integrating over an infinite surface. Okay, but this turns out to be zero, and the argument goes this way. So as R approaches infinity, let's look at everything under the integrand. How does it change? So as R approaches infinity, what happens like in the universe? As you go towards infinity, all charges in the universe from infinity look like a point charge, right? Right, because you're leaving everything behind and you're going towards infinity. All charges in the universe, whatever they are, get close together and they look like a point charge. Because they look like a point charge, what's the field for a point charge? The field for a point charge is, remember, it's Q over 4 pi. There is no epsilon here because this is d R squared, right? So as R equals infinity, d, let me take magnitude of d, is proportional to 1 over R squared. Okay, as R goes to infinity. What about V? Again, everything looks like a point charge. V for a point charge is Q over 4 pi. I think there's an epsilon and it's R. So it's proportional to 1 over R. And this is what makes the difference as R goes to infinity. Because now the product VD is proportional to 1 over R cubed. Okay, so we're integrating something that's proportional with respect to R cubed. Say at infinity, this becomes constant everywhere. It becomes like a point charge. So it's a sphere at infinity. We can take this out of the integral. So the whole integral becomes proportional, right? So what's inside the integral, we can take it out at infinity because it becomes constant. Everything becomes like a point charge. So the energy is proportional to 1 over R cubed, but then you have to multiply by the surface at infinity. What is the surface area? Well, the surface area for a sphere is 4 pi R squared. So area is proportional to R squared. Okay, so ultimately, this whole integral turns out to be area times V times D, which is proportional 1 over R cubed times R squared, which is proportional to 1 over R. So the integral, this integral, SVD dot ds, its value is proportional to 1 over R. So as R goes to infinity, this whole integral goes to 0. Okay. So this thing is 0. This thing goes to 0. Okay. Because this thing goes to 0, we end up with the fundamental expression of the energy in the electrostatic field. Based on just the field itself, So it's going to be half. And this makes sense. The field is a physical entity. The field itself contains energy. The field doesn't need any charges. Even if you are, like, I'll give you an example. So this is the energy in the electrostatic field. Like, for example, radio waves, television waves, or radio waves, radio transmissions. Regardless of the currents and charges that cause them, EM waves themselves propagating through space carry energy. That's why radiation, like when people get treated for something with radiation therapy, the field itself that hits your body carries energy, dumps energy into your body. Many heating elements in ovens are infrared based. A lot of times it is the infrared energy that is dumping energy into whatever you're cooking. Of course, the biggest example is the sun, right? The fields, the light coming from the sun is an electromagnetic field, and it carries energy. So energy is carried in the field itself. The field itself has energy, and the way that you express energy in the field directly from the field, without having to kind of resort to thinking about potential energy or thinking about charge distributions and how you configure the system, just the field by its very existence inherently has energy. Similar to how a particle by its very existence either has a kinetic energy or a potential energy. Of course, the energy in the electrostatic field is analogous to potential energy. Okay, we can write this in other forms. We have to remember that D equals epsilon E, right? So what is D dot E in this case? Well, it's epsilon E dot E. What happens to a vector when you dot it with itself, right? A dot A is just the magnitude of A squared. So this is epsilon E magnitude squared. I use shorthand notation where magnitude of a vector is just the symbol for the vector without the arrow. That's a notation that I use. So this is, I think the book uses this too. Okay. So W equals half rho V. So I'm just getting rid of the vectorial form. So this becomes epsilon E squared dV. I choose to keep the epsilon under the integral. Someone might argue, why don't you take the epsilon out? The epsilon doesn't necessarily have to be constant, because the epsilon depends on the medium. So in space, you might have different mediums with different epsilons. So this might be epsilon 1, epsilon 2, epsilon 3, epsilon 4. This might be epsilon 0, vacuum. So the epsilon has to go inside the integral because, well, just to remind yourself, because if you put it outside the integral, you might think that this is it and it's outside the integral always. No, it's not always outside the integral. It is inside the integral unless it's constant, then you can take it outside the integral. So here we're integrating something over all of space to get total energy. This suggests that this thing in here is some sort of density, right? Whenever you take something and you integrate it over space, like mass density, you integrate it over space, you get mass. Charge density, you integrate over space, you get charge. This suggests that this thing here is an energy density. So this is a measure of joules per meter cubed, right? So we can define a new variable, new quantity called the energy density, small w. So small w is the energy density, and we define it as half epsilon E squared. I could write E equals D over epsilon. Sorry, I think E. Yeah, epsilon E is D, so D E is D over epsilon. So this becomes also half D squared over epsilon squared, so it becomes D squared over 2 epsilon. It's equivalent, okay? Joules per meter cubed, not squared, cubed. It's over space, okay? By the way, we could also use the argument that remember in the previous form of the energy, half rho V dV, we could have argued that, hey, rho V is also an energy density, expression of the energy density. It's a curious thing that in an energy equation, it always half appears. So even in kinetic energy, it's half mv squared, right? So this curious half keeps appearing when we calculate energy. And this half comes from the symmetry of the configuration. In mechanics, this half comes from the symmetry of, if you have like the origin, if you have two particles and one particle is going up at a velocity v, this is equivalent to this particle being stationary and the other particle moving away at velocity v. Because those two configurations are completely equivalent, that's the reason the half appears Okay, so this is similar symmetry arguments where we said it doesn't matter what order we will bring in the charges, causes this half to appear. Let's check the units. Okay, so check units to make sure that what we're doing here is same, right? So let's check the energy density. So the energy density, small w, has units of what? Has units of epsilon, and then unit of E squared. What's epsilon? We said epsilon is farad per meter. What's E? E is volt per meter, the whole thing squared. Okay, so this is what? So this is meter squared times meter. This is meter cubed. We already got the meter cubed. Good start. And then we have F times V, and then another V. What is F times V? So remember, for capacitance, C equals Q over V. So capacitance times V is charge. So this thing is charge, is Q, is Coulomb. What's Coulomb times V? So remember what we define voltage. Voltage is the energy per unit charge to bring a charge from infinity to a certain point. So really, V is W over Q. So V times Q is energy. So this is, sorry, charge times V is energy. So this is joules. This equals joules over meter cubed. Okay, so the units do make sense. Okay. So this is pretty simple, actually. This is a simpler calculation than taking the charge density, multiplying it by V and integrating it over whole space. This is just taking two vectors and the same vector and dotting it with itself. Like, for example, let's take, okay, this is an interesting example. This is true, by the way. This is true, but classical electrodynamics is kind of like, although from the beginning, from day one, we always study point charges, and we study point charges because they're simple to study, right? Because everything, if you stand far away from it, it looks like a point charge. The thing is, point charges are not practical systems. The reason is that you will discover that if you take a point charge, what is E for a point charge? E for a point charge, let's take it in spherical coordinates. E for a point charge is Q, charge Q, over 4 pi epsilon naught r squared r hat. And what's D? D is sorry, did I make a mistake here? I think, oh yeah, I included the half, that's good. Okay, D is Q over 4 pi r squared. The difference between E and D is just the epsilon. What is half E dot D? What is the energy density of the field of this point charge? It's half E dot D. What's E dot D? R hat dot R hat goes away, it's 1. We end up with Q squared over 4 pi epsilon squared. That's fine, that's a constant, r to the power 4. Right? So this is the energy density. So you might think that's fine, you know, the energy density around space. So this is the energy density at every point of space. So you might say that's fine. What about the total energy? Total energy is the integration over all of space, including to infinity, of half E dot D, dV. So this is going to be, let's take the constants out. This is going to be Q squared over 4 pi epsilon naught squared, integration over all of space of dV over R4. Okay. Yes.
Are you missing a half in the 1/2 times?
Yeah, there's a half here. Good, thank you. Right. Now this might look like something where it's fine, you know, at infinity this goes to 0. This integral should converge maybe. The reality is that this doesn't converge. Okay. And the reason it doesn't converge is because you're integrating from r equals 0, and around r equals 0, this integral goes to infinity. So if I plot this 1 over r to the power 4, it's gonna go, it starts from infinity and goes down like this. But trust me, this goes to infinity. Okay, this goes into infinity because the field gets denser and denser and denser. The field of the point charge, really close to the point charge, has infinite energy density. Right? So this goes to infinity. So the electron, not the electron, sorry, a point charge is a configuration that has infinite energy. And the reason it has infinite energy is because it's not a practical configuration, right? And the reason it's not a practical configuration, because how do you build a point charge? How do you build? You have to bring a bunch of this charge distribution and compress it until it gets up to a point. But the problem is, as you compress and compress and compress, hey, the Coulomb, are you looking for a certain class?
No, this is ECGR3121.
What?
ECGR3121.
Oh, okay, cool. If you compress the charge density smaller and smaller and smaller, you'll get extremely stronger Coulomb forces that work against you. It will require you an infinite amount of, if I have a charge distribution, rho v, it will require an infinite amount of energy to crash this rho v into a point charge. That's why point charges in the theory are mathematical idealizations. They're not practical. Even the electron, which is the smallest charge there is, has a diameter. The final thing I want to cover on electrostatics is the principle of virtual work. Okay. This is similar to mechanics. In mechanics, we could work with Newton's law directly, work with force directly. But then we can define something in mechanics called mechanical, not mechanical, potential energy. And then we could say, we can derive the force from the potential energy. So F equals minus du over dx. And the idea when we look at stuff from the perspective of potential energy, we notice that physical systems, we observe that physical systems tend to have the property that they're always attracted to the point of minimum potential, right? So the force here in this region is going to be pointing in this direction, you know, minus du over dx. Du is decreasing, so this is negative, so it becomes positive, and the force in this region is pointing towards this direction. So the forces act, if you have the potential energy over space, the forces act in a way such that they bring your system, try to bring your system to the point of minimum potential energy. Like everything rolls downhill, for example. If you jump from a building, you fall down rather than up. This sort of thing, right? So the system will always naturally move towards the state of minimum energy. We said in electrostatics, the field itself represents energy, holds energy. So analogous to this, same thing in an electrostatic system. The system itself tends to lower energy states. Lower energy states means less field, essentially. The field always tries to dissipate. If you vibrate something, you get a wave. The wave moves away from you. right? And around you, things go back to zero. If you have two charges, the charges try to repel each other so that the field goes everywhere to zero. The charges get really far away from each other. So the system always tends to minimal potential energy. This allows us to kind of describe a force in different way. We can describe a force, or this allows us to determine the force in electrostatic systems in an easy way, just similar to this. Just understand how the energy changes when you change the system, and that change in the energy should give you the force. Not a real change, by the way, a virtual change. So let's say this is for a mechanical system. This is my potential energy. This is X. Let's say my particle is here. What I can do is I don't know how the particle is going to move. What I can do is I can assume that the particle is going to move in this direction, right? Displaced by this amount. But this is not a real movement. This is like a conceptual movement. This is like I imagine that the particle moved this amount. This sort of thing is called a virtual displacement. The particle didn't actually move. In my mind, I thought, what would happen if the particle displaced this amount, right? And then I calculate delta U if the particle displaced this amount. If there is a delta U, then there's a force. If this is like something like a flat surface, there is no delta U, there is no force. The particle will do nothing. The particle will sit there, okay? So similar to that conception, similar to this way of looking at things, we can look at a system of charges in a similar way. We can take a freeze frame of the system and say, okay, the field looks like this. The total energy looks like this. What happens if I displace something by a virtual displacement, small virtual displacement? How will the energy change? If the energy changes, then there's a force happening. If the energy does not change, then there is no force. So this is in essence the concept of virtual work. So the idea is something like this, right? So virtual work. The idea is that you have a force, you have a force field, you have something, and then this particle, whatever, you virtually displace a distance L. You don't actually displace, but you think, what would happen if I displace it? That's what virtual means. What happens if I displace this particle by distance L? W would be FL, right? Force times distance. The force that the work that this force field does, right? On this particle. So let's make this differential. Let's make this like a small movement, small displacement, DL. So dW in this case is going to be, let me write it more properly. It's going to be F dot DL, right? So in an electrostatic system, F dot DL, F would be the electrostatic force, the Coulomb force. DL is going to be displacement of charge by field, right? So this is F dot DL hat, we could say, times DL, right? Right. So what happens? I have a field, I have a charge. If the field itself displaces the charge moves away, right? So naturally, the field tends to go towards the state of minimum energy. The charges tend to want to spread apart from each other. If they are opposite signs, they tend to want to attract each other. But the point is that ultimately the field is going to get smaller. So the system, the electrostatic system, is going to lose energy. So it's telling me how much energy, if the electrostatic force moves the charge in a direction, small direction, this is how much energy the electrostatic field loses, minus dE. Okay? The system always wants to go to a minimum energy state. Okay? So let's take this we want to apply now the concept of virtual work. So the way we think about it is as follows. Let's say I have a system, I have a field due to some distribution of charges, whatever they are, right? And then I have my axis. My axis representing the space. Let me not draw the axis now. Let me just draw the field, some electrostatic field. It doesn't have to be a uniform straight field. It could be like a jumper, whatever it is. But then I have now a part of my system that can move. This is a charge Q that can move. What I can do is I can build a coordinate system around this particle and then tell myself, ask myself, what are the degrees of freedom? That's the other thing in trying to determine virtual displacement. You have to understand what the degrees of freedom of your system are. In a car, the wheels of the car have only 1 degree of freedom. They can only spin. Something like a pendulum has 1 degree of freedom. It can, do this. If you have a double pendulum, it has 2 degrees of freedom. It has 2 angles. Right? So when you try to solve a problem using the technique of virtual work, you have to understand what are the degrees of freedom of the system. The degrees of freedom of the system, essentially a charge lying in an electrostatic field, are 3, because the charge can move in 3 different directions, right? So it's a 3-dimensional degrees of freedom. Okay? So the question is, what happens if the charge is displaced virtually, some displacement d? How does the electrostatic energy change, right? And there's a way to do that, right? So we can plot WE for displacement with respect to displacement, right? So WE here, if the electron, if the Q moves to this point, this is what WE is going to be. If the charge moves to this point, this is what WE for the whole system is going to be. So we can describe in 3-dimensional space how does a function of the energy of the whole total system with respect to the displacement in 3-dimensional space. The change of energy is the force. What is the change of energy in this case? What is the directional derivative in this case? If you have a 3-dimensional problem, it's the gradient, right? So it is the we can say that dWe equals let me see, gradient WE. Sorry. Did I misplace causes DL? Oh, okay. Yeah, no, this is correct. This is correct. There is no minus sign. It's just the gradient. Okay, so you take the displacement, you multiply it by the gradient, you get the directional derivative. You get how the energy changes, right? It's important here to think for problem in this perspective. You're essentially the gradient is not over real space. The gradient is over the displacement space of the part of the system that can move. So the virtual movements available to this part of the system are 3-dimensional. And then the rate of change, directional rate of change is the gradient. You dot it by the actual virtual displacement, you get the dE. So we go back now to this equation. F dot dl is minus dWe. So F dot dl is, I can take the minus n minus grad WE dot dl. So this tells me that the force has to be minus the gradient of WE. WE is the energy, complete energy of the system. So this gives me the force in newtons. Okay, and this is an alternate way of calculating the force. You might say, why bother with it? You know if you have a point charge, you know what the force is. You first calculate E. This is useful when you have a system that is too complicated for you to do this, right? Say you have a system, a macro system that is too complicated to do this, and sometimes it's easier to just calculate the total energy of the system, right? And then find the force. So in many applications, doing something like this is easier. I'll show you an example. You might have a complicated system with a lot of objects, let's say, but you know the field, and then you have a wire, and you might say, hey, what would happen if I displace this wire? What is the force acting on this wire? It might be complicated to calculate the force directly, but what might be easier is for you to displace the wire, a virtual displacement, calculate the change in the field, total energy in the field, and use that to calculate the force. And this can also quickly lead you to answers. Like, let's say I have two parallel plates, two infinite parallel plates. You can get answers without even doing any calculation. So this is positively charged. This is negatively charged. And say okay, to those plates, let's say those plates are prevented from combining with each other, right? There is some material here, but someone might worry, could there be a force that causes those plates to slide? Would this force, with this bottom plate cause the top plate to slide away? Well, you could say, well, what happens if this virtually displaces to the right? How does the field change? That's the question you need to ask yourself. If this top plate virtually displaces to the right, the field inside remains the same. Because the field inside remains the same, the total energy remains the same. Because the total energy remains the same, there is no force pushing the plate to the right. Do the plates tend to want to stick with each other? Well, then you ask yourself. So I have E here. What happens, and the property of a parallel plate, the infinite plate property, is that there's no E outside the plate. Okay. What happens if I displace the top plate lower? I get a smaller D. So I have less volume between the plates. I have less energy between the plates because I have, so energy is just E dot D multiplied by integrate over the volume. When I compress the plates together, displace the plates closer together, I have less total energy between the plates. Because there's a change in energy, there is a force. So yes, there is a force that tries to push the plates together, and that force is kind of pushing the plates towards each other because that's the direction where the energy is minimized. That's the direction. The force doesn't try to pull the plates apart. The force tries to pull the plates together because that's where energy is minimized. Of course, you can, I leave that as an exercise, you can derive Coulomb's law from this too. I mean, you can, if you start from, so if you have a Q1, let me see, come on. Let's say everything you know about electrostatics is just from the energy concept, right? So you can easily derive Coulomb's law. If you have Q1, Q2, and a distance R between them, and you just calculate WE, WE is half Q1 V1 plus Q2 V2. So WE is half Q1 Q2 over 4 pi epsilon naught R. If Coulomb's law does not result from this, then everything we're talking about doesn't make sense. It's not consistent. But we will discover, so this equals half plus half, so this becomes 1 Q1 Q2 over 4 pi epsilon naught R joules. Okay. So say we center our coordinate system around Q1, and this is R, and this is Q2. If we take F minus gradient WE, and I mean, this is easy to see. We're going to get, because gradient involves D over dr. when you differentiate d over dr, 1 over r by d over dr, nothing else is going to be involved because there is no theta in here. You get 1 over r squared. Minus. You get minus 1 over r squared, and the minus sign cancels the 1 over r squared. One last example I want to give you where it is clear why this method is superior many times. Motors. We haven't studied the magnetic field yet, but it is the same concept. How do you determine the torque of a motor? All you know, so the motor, you supply current to the motor. This generates a magnetic field in the air gap between the stator and the rotor. The rotor is the part that can spin. How do people easily determine the torque? How do you approach calculating the torque? This is a complicated problem. I mean, this is a three-dimensional thing with a lot of metal, and if you want to go by it by element integration, this is going to be complicated. What people do, and the easiest way to do it, is to calculate the total energy, in this case magnetic energy, in the air gap, and ask ourselves, what is the degrees of freedom of the motor? It's spinning it. We can spin it to the clockwise or counterclockwise. So you ask yourself, what happens if I displace the rotor virtually by a small angle? Does the total field, does the total energy, field energy inside the air gap change? If it changes, then yeah, there is torque. Yeah, because torque is a force. So it's going to be minus grad of the change of the energy. If you rotate the rotor, displace it a small amount, and the field does not change, remains constant, there is no torque. Right? So this is kind of like an easy way to, I mean, without this method, calculating torque on a motor is going to be like a really difficult problem if you want to just go back to the Coulomb's law or the Biot-Savart law or whatever. All right. So with this, we conclude electrostatics, right? So next we will start with, well, we're just gonna do magnetostatics due to, well, we want to deal first with constant currents, right? And then we will start dealing with magnetostatics and build up magnetostatic theory similar to what we did with electrostatics. All right, everyone. Thank you.